All right, slides have been posted. Let's get started. So today's lecture will cover two topics. We'll get into penetration testing, so that's the actual hacking part of hacking, so messing with computers rather than just messing with data or information, as we've been doing so far. But in order to get a good understanding of how to do penetration testing, we first have to talk about what servers are, right? Penetration testing is the art of finding holes in servers, so we first have to talk about how you can do that and how things work at the network level. All right. So just as a kind of review, maybe, a host or a PC or a computer is any device that is at the edge of a network that sends and receives internet data. Right now I'm using Ethan's laptop, that's a host. Right now a lot of you have your own laptops out, those are hosts. When you go and access google.com or Wikipedia, you are using your own host computer in order to access some server on the other side of the internet, right? You can go in and type on your laptop, ping google.com, and it'll send a single packet, or it'll send single packets from your laptop to Google servers, and hopefully they'll be received, and that will work out just fine. Laptops, phones, PCs, printers, the things that we're using right now all count as host devices. And the entire point of the internet was to connect these devices together, right? It was to make it so that you can use your laptop to access YouTube to watch whatever videos you want. And on either end of that connection are two hosts. One of those would be your laptop or your computer or your phone or whatever else it might be. And on the other end of that connection is the server that you're contacting, YouTube servers. A server is a PC or is a host that provides some useful internet function. So in the case of YouTube, it's providing video streaming, right? So there's a couple steps in that process. The first step is you first have to access YouTube through your web browser, which means that YouTube servers are listening on the web ports. Web is HTTP, HTTPS. It's that thing that you see at the top of the search bar whenever you access any website, right? And there's a bunch of other steps in there that make the whole YouTube process work just so seamlessly, right? Like their server is contacting, if you have an ads on a video, it's contacting many other servers to receive those ads based on marketing choices. And there's other servers in YouTube's own backend that are hosting just those videos so that they can serve those to you. So the entire process of serving a website is somewhat complicated, but it can be simplified to you are using your own laptop to communicate with servers or any number of servers on the other side of the internet. A router is a device that exists kind of in the middle. I'm really just mentioning this for more context, but this isn't totally relevant as far as I'm concerned. The entire function of a router is to route data across the internet. So when you are using your own laptop to contact some server, that packet has to be routed, right? Just like how when you put mail into a mailbox, if that's something you still do, then your mail has to get from your house, well, first from your mailbox to a postal facility, all the way to the end to your recipient, right? So a router is kind of like a postal service. It's doing the moving. It's moving your packages from the mailbox to a postal facility, to the next postal facility, to the next one. So for example, if you're in Davis and you send mail to Chicago, then the package that you have will first get probably sent to Sacramento, then to, I don't know, like maybe Salt Lake City in Utah. It'll keep going east until it reaches its destination, right? The postal facility is doing this job of moving your package from postal service to postal service en route to its destination. And the entire purpose of a router is to do this exact same thing. So earlier I mentioned, ping google.com. I believe this should work, right? Yeah, you can just send a ping to google.com and that'll work just fine. Feel free to try that on your own laptops. Just pull up the terminal. And there's another command that you can try that's sort of similar to this. Actually, I'll give it a moment just to let everyone open their terminals if they aren't open yet. I always like to comment on the latency. I know we complain about EduRoam a lot, and it's not good, but it has really good latency. Like I tried this for my own home, and maybe because of the different types of Wi-Fi routers that they're deploying here, latency is just pretty good when it works. There's another command that you can try. So you can first try ping google.com, and that'll send a packet down to, I don't know, San Jose or whatever. And it only takes 8 milliseconds. Like I could send how many of that in a second? Like 100 in a second, and it would, or 125 in a second, and it would work just fine. We can also try traceroute. So if you're on Windows, the command is traceRT, or if you're on WSL, or if you're on Linux, or you're on Mac, then type it fully out, traceroute, and then type google.com, and hit enter. Does it work for Google.com? They might have it blocked. I'm not actually sure. Oh, it does. Okay. Give it a moment.
Assuming that my computer has these programs.
I think macOS has it by default, to be fair.
Don't have it, just install it.
Yeah, actually, there's some Linux systems that won't have it by default, and you have to install IP Route 2 or something like that. I might be getting that entirely wrong. Anyway, okay, you can see it's fully done that process. What does this output mean? Remember, as I just mentioned, the entire idea of a postal facility moving packets from facility to facility, so like from Davis to Sacramento to keep going east to Salt Lake City and then so on. In the same way, when you're sending a packet on the internet, it's doing the same thing, right? Your packets are moving from your computer to a router to another router to another router and so on. And so when you run trace routes, it's kind of the name, you're tracing the route of a packet, so you're finding all of the different routers that your packets are going through. So right here, this is most likely just the access point that's in this room. I can point it out, it's over there on the roof, on the ceiling. And you can see that there's a bunch of other IP addresses here too. So you can see one here. You can see this one literally says UC Davis in it. These ones also say UC Davis in it. This one too, and so on. And you can see scenic.net. Scenic.net is UC Davis's internet service provider. They are the California Education Network or something like that. And there's a bunch of other hops until it finally, it ends the transaction because it reaches its destination. So yeah, any questions about what that output means? No? Yeah. So you can also see the latencies here, like between this laptop and the access point up there, it's about 5 milliseconds, and the entire path is only about 10 milliseconds. So just know that like the path from my laptop to the access point it takes about the same amount of time as from this access point to San Jose. So that's how optimized the internet infrastructure really is, in certain areas anyway. Okay, so network interfaces are the part of a device's hardware which allows it to connect to a network. Sometimes you can see it on the outside of a laptop. Like if your laptop has an Ethernet port, mine does. You might have right here. You can see it right there. That's the network interface. It's some type of hardware that allows your computer to connect to the internet. For the rest of us who generally use Wi-Fi, we will have a Wi-Fi card within the laptop. So for devices that use Wi-Fi, there's a Wi-Fi card that's just inside of your laptop that you can't see from the outside, most likely. And there's some very old computers that don't even have a Wi-Fi card, and so you need to plug in a USB device. So it's a USB-enabled network interface card. Every computer that's connected on the internet needs some way to be on the internet, and so network interface cards are how they do that. My laptop has a Wi-Fi card inside as well as an Ethernet port on the outside, so it has two network interface cards. If you have desktops, most likely they have the same situation there too. A link is what we call the connection between interfaces. So when you're on a Wi-Fi connection to EDU room like you are right now, you have a Wi-Fi connection, a Wi-Fi link between your laptop and the access point up there. So these are all network interfaces. You can see, like I just pointed arrows towards all of them. Those are all individual host PCs, and then that's a router in the middle. Yeah. Here's another demo. So if you're on Windows, type ipconfig in your terminal, or if you're on WSL or Linux or Mac OS, type ifconfig. I'll do that right now. Are you on the VPN or are you fine?
I'm not on the VPN.
Okay. So, let's see. There will always be one that refers to, that'll have some type of indication that it's wireless, and I forgot how you can tell if it's on Mac, but...
WS?
Is it WS?
I believe that's the wireless on mine.
Do you see it?
It's probably in 0.
EN0, yeah.
Yeah, it's
that
in
does look
0.
right.
Where's EN0? Yeah, that's the one.
Okay, here we are. You can see this IP address over here. Okay, wow.
What?
I just scroll down. Okay, you can see an IP address over here. I won't highlight, which makes it harder to see, but hopefully I do this.
You have a question?
Go for it.
Isn't ifconfig kind of fabricated on Linux?
On Linux, yeah. So if you're on Linux, you should use IP address. IP space address. It's not. I don't think Mac OS has it. I don't believe so. IP address. Yeah. It exists on Linux. I would recommend using that. The output is a lot more clean, but for consistency, I just continue to suggest using this because it's the same on Linux, on Mac. I'm holding myself back for the Mac OS users. That's right. So there's an IP address over here. We'll talk more about how to interpret that. You can see netmask over here, and then broadcast we're going to ignore. So yeah, these are just looking into your own laptops on the Eduroam connection, your own IP address, your own netmask. These are all private IP addresses, which the meaning of that isn't super relevant, but the point I want to get at is that we're showing this IP address, but that's not the same as like getting doxxed, like in that sense. That's an aside. If you have questions about that, we can talk about it after class. Okay, each interface has a MAC address, and then in-use interfaces should have an IP address. So you can see this Ethernet address that refers to the MAC address. Every interface has one, but not every interface has an IP address like it does here. So a MAC address is a hardware address that specifies the specific, it's tied to your network card essentially. So on each of your network cards, again, I have an Ethernet card and I have a wireless card. And so each one has its own MAC address that's burnt into the hardware when it was first created in the factory. Okay. Packets we kind of already talked about, but the point I want to emphasize is that they move step by step across the network, and each step gets the packet closer to its destination. Any questions so far? Okay. So in the same way that packages can only be routed to buildings that have addresses, packets can only be routed to devices with IP addresses, which is why it was pretty crucial that the interface that is currently connected to Eduroam has an IP address. If you had an interface that didn't have an IP address, that means you're not connected on Wi-Fi at all. And if you want to go ahead and try it, you can first run ipconfig or ifconfig or IP address, depending on your operating system, while connected to Eduroam, and see that there's an IP address. And then you can disconnect from Wi-Fi, and you'll see that it's now completely gone. You can reconnect and it'll be back. Without having an internet connection, or vice versa, without having an IP address, you cannot have an internet connection, and vice versa. So here's just a simple example of an IP address. It's like the most commonly used one, and most likely it's what you have in your home. 192.168.0.1. It's a structure of 32 bits stuck together, or you can think of it as 4 groups of 8 bits, or 4 groups of 1 byte. So each of these numbers separated by the period represent 1 byte, or 8 bits. And again, these identify internet devices. We can write it into binary just to see it a bit more clearly, and this will come into play in a couple of slides. But yeah, it's really just doing a direct decimal to binary conversion. It's nothing too out of the ordinary. So on this output, we also saw this thing called netmask. I believe on Linux or on Windows, it should display as kind of in the same format as this IP address, but right now we see it in hex. It says FFFC0000. They define the size of a network. So when you're on a network, and we are all currently on the Eduroam network, we're all connected to the same access point, so we should all be on the same network. Devices can communicate directly with one another. So for example, when you're at home and you're using your printer, your laptop or your computer is sending packets directly to your printer. It's not getting forwarded through a router. Like remember how we ran traceroute and we saw that there was this whole list of hops that we're going through, right? Because we're sending packets from Davis to the Bay Area. When you're sending packets directly on a network, you won't see all of those hops. In fact, what you'll see is if you try tracerouting your printer's IP address, all you would see is that one hop that's your printer. It would go from the, let me just pull up the traceroute again and just point at it. So here we see the first hop is the router up there. But if you're again, it's scrolled. If you're tracerouting your printer, you would see the first hop is your printer, and that would be the end of the route because it's directly connected. You're right next to each other. You don't have to yell at it. It's like right there. So in the same way of like if you're sending an envelope to someone who's in your own house, then you would just hand it to them, right? That would be the one person that you're talking to. You're not talking to the postal service. You're just giving it to them directly. And this is a pretty important concept in computer networks, communicating on a single network, because as crucial as it is that routers are connecting networks, at the end of the day, what's happening is a bunch of different series of devices within the same network communicating to each other. So when I send a packet to google.com, my laptop is communicating to that router up there, which is on the same network. And that router is communicating with another router, which are each other on their same network. And that next router is communicating with another router that's on the same network as itself. Does that concept kind of make sense? Any questions about that? All right. So a subnet mask identifies the size of a network. Here's how we can kind of interpret it. So there's a rule with subnet masks that there are always a continuous stream of ones followed by a continuous stream of zeros. It will always be that way. So you'll see ones on the left side, on the left-hand side, and you'll see zeros on the right-hand side. Every subnet mask is structured that way for a specific reason. You will never see zeros in the middle of a block of ones. You'll never see ones in the middle of a block of zeros. The ones represent network bits, and the zeros represent host bits. What does that mean? So here's that IP address we had earlier, and now it's a subnet mask, and I've put it into columns so that you can see the relationship between them. So again, the blue part, the ones represent the network portion. Any IP address that shares the same network portion is on the same network. So for example, 192.168.0.2 would be this IP address. Right? Let me modify it here. You just type 10. And this is 2 in binary, right? So this would be 192.168.0.2. And that's on the same network as 192.168.0.1. Because it's only the host part that's changing. It's not all of this blue part is staying the exact same. If you had 192.168.0.30, which I don't actually know what the I'm just gonna guess. That might be 30, I don't know. If again, we're only changing that green part. The rest of it stays the exact same. By the way, if I'm correct, please let me know, because that would make my ego feel really good. So the green part is changing, the rest of it is staying the exact same. And so this is another IP address that is, again, on the exact same network. What wouldn't count as being on the same network is if you change this blue part. So for example, if you change the IP address from 192.168.0.1 to 192.169.0.1. So if I just change this bit here, that would be 169, and that's now a different network. And so it's completely on a totally different network as the original IP address we had. If you change the first number to 200, then again, the blue part is different, it's on a different network. And you change this third number, again, I'm just saying the same thing over and over, but again, it would be on a different network because that blue section is changing. And this rule applies for any different type of subnet mask that you use. So again, a subnet mask is a stream of ones followed by a stream of zeros. So let me just make a copy of this and as another demonstration. So let's say I instead had 0, 0, 0, 0. So again, it's a continuous stream of ones followed by a continuous stream of zeros. And now this is part of this is the network part, right? This would be a 240. I might be wrong, but I think that would be a .240 if you're just converting it back from binary into decimal. And so now we had this IP address, right? So 192.169.0.1. Oh, sorry, bad example. We had this IP address over here, right? 192.168.1.1. So right now, what we have written here is 192.168.0.1. If I change it back. 192.168.0.1 is written here in binary. Now, if we change this green section to update it to look like this, 192.168.1.1, all we have to do is change this number to a 1. Now, the green part is the same, the green part is different, but the blue part is the same as what we had before, right? So this subnet mask has adapted in such a way that it now works. Now this IP address is on the same network as this IP address. And it's all because of just the subnet mask. Any questions about that? Subnetting tends to be one of the harder parts of computer networks, which is great because it's right at the beginning. So, yeah. That was sarcasm, but it is right at the beginning. Yeah.
So I've also seen it written as like /24/32. Like, is there a reason why it's like cannot be like written out in this like logical thing?
It's this was just for the purpose of instruction. So the let's talk about that. That's a good point. So sometimes you'll see. I'm going to repeat myself again, but a subnet mask is a stream of continuous ones followed by continuous zeros, right? And so there's a shorthand way of representing a subnet mask, which is just by counting the number of ones. because there's only one combination for each number of, like if you know the number of ones, then you know the subnet mask, because it's a string of ones followed by a string of zeros. So this right here, this 255.255.255.0 is 8 plus 8 plus 8 ones, right? Or 24. And oftentimes we'll denote that as 192.168.0.2/24 to refer to the whole, sorry, I got smaller. To refer to the whole part. Because the /24 can only refer to this type of subnet mask, because we know that 24 refers to the number of ones, and it's always a number of ones, or it's always going to be a string of ones followed by a string of zeros. Every subnet mask must be 32 bits in the same way that every IP version 4 address must be 32 bits. So if you know the number of ones, then you know the number of zeros, therefore you know the whole subnet mask. So your question was, is there a reason why we write it out fully rather than... I would actually change it and say that we tend to write it out in this format because it's just convenient. It takes up less time to, like, you don't have to, it's less to type out, essentially. And so when we're doing the pen testing stuff, we'll show some, like doing network scans and stuff, I believe, and you'll see it generally written out in the slash notation rather than writing out the entire IP address, because it's clearer to the eyes, essentially. And as you know, for the sake of experiment, we can just do the same thing here. So what would be the slash notation for this IP address? Right. I didn't do the math in my head before I asked, but yeah, it would be 20. So you could write this IP address as 192.168.0.1/20. So again, this is like a notation to refer to the entire network. So if you wanted to, again, we're going to talk about this more in a little bit, but if you wanted to run a scan across an entire network to see what kind of computers are running on that network, then if you wanted to refer to the entire network, you could say like scan 192.168.0.1/24, and that would say scan every computer from 192.168.0.1 to 192.168.0.255, right? So this would be on the same network because, again, it's only that third number, that green part, that's changing. If we were talking about a /20, then this would include 192.168.0.1 all the way to, I think it might be .15.255, because you can vary these last 4 bits, and this should, like if you turn this to 1111, that should be 15, I believe. Yeah. Cover.
When we use like the slash notation, does it matter like the bits of the address that are inside the green portion?
Okay, good question. So it will not matter. And let me just add a new slide on the go, because I think this is it's a good conversation to have. Time check. Are we all right, or do you think? Yeah, go ahead. Okay. So 192.168.0.1/24. Actually, let me just copy paste this. So there is a canonical type of IP address. Well, actually, let me first write out. So 192.168.0.1/24 is what we have, right, going into this. So this is one way to refer to the entire network, but the kind of like canonical way of referring to it is by taking any zero here, like all of the green part, and basically copying those zeros into the IP address, so turning it into that. So what would be this IP address if you just like say it out in decimal? You can use the format we had here, so it should be somewhat similar. Just think about what changed between, yeah.
192.168.0.0.
Correct, yeah. So all you're doing is changing this last number into a 0, right? The rest of it was basically all the same. Does that make sense? Yeah. So the canonical way of referring to this network is as a 0. So just setting all the host portions to 0. You can think of it as doing a bitwise AND. So if you AND anything with 0, it'll output a 0, right? Because the only thing that outputs a 1 from a logical AND is 1 and 1. So if you AND the subnet mask and the IP address, what you'll get is that all of the blue portion stays the same, and all of the green portions turns into zeros. We can do another example with this subnet mask here. So let's say you wanted to find the canonical name, this is kind of a boring exercise, and you'll see why. You want to find the canonical name for this IP address, or for this network. So again, it'd be 192.168.0.1/20. Someone other than 1Kai. Do you want to say, like, go ahead and say what the canonical name for this one would be if you do the same thing of turning all those green bits into zeros? Technically, it was 15. So again, I get what that came from. It's a little bit wrong still, but just think of it turning all of these zeros into turning all of this green part into zeros here.
Can everyone see the slides? Okay.
Yeah.
Is it 192.168.120?
Dot one.
Dot 120.
Dot 120. How did you get that?
I mean, you said and the green parts together, right?
Yes.
So you're ending all the bits together.
Or all of the bits, but yeah. So
Corresponding. The result should be like, I don't know, the green is like 1 0 0 1 0 0.
oh yeah, maybe I should explain what the and is. So essentially, you're taking these, like each corresponding bit, you would and them. So did anyone else have their hand raised? I didn't see, but yeah.
192.168.0.0.
Yes. So that's why I said it was a boring exercise, because it was the exact same as what we had earlier. So you turn this into 0 and turn this into 0. And let me explain why that is. So when we're doing this and, we're looking at each column individually. Maybe I should have explained that before, actually. But yeah, we're looking at each column individually. And so let me write it in purple, or whatever color this is. So we're looking at each column individually. So what is 1 ANDed with 1? 1, right? And then the same thing again. What is 0 ANDed with 1? 0, right? And we can just keep going. Dot. Let me change the font. It's not monospace. Okay. Dot. And then 1 ANDed with 1, 0 ANDed with 1, 1 ANDed with 1. And the pattern you'll see here is that basically the entire blue section gets carried over directly, like 1 to 1. So we see 1, 0. Oh, I realized I changed this into 169. Let me change it back. 0, 0, 0, dot. And then the blue section again stays the exact same. And see here, we now have all of these are zeros where we've entered the green section, the hosts section, right? And all of these are, kind of random bits. This says 15.1. But if we do an and again, like what is 1 ANDed with 0? 0. 0, 0, 0. And then we can do the same thing here again. So it's 0 ANDed with 0, which of course would be 0, 4, 5, 6, 7, and 1 ANDed with 0, and like we said, is 0. And so all of these bits all get turned into zeros, right? So the entire green section gets turned into zeros essentially, because we're doing this and with a 0. So when you're finding the canonical name for an IP address, which for a network, you essentially keep the entire blue section and turn all the entire green section into zeros, because that's just what the logical and does. Any questions? Did that clear up the confusion? Cool. All right. Okay, so a service, we're getting more into the more pen testing side of things now. A service is an application that is running on a computer which operates over the network. So there's something that you can kind of try on your own laptops. I assume that everybody has Python installed from previous classes possibly. Do this in a clean directory for sure, because what you'll be doing here is hosting a web server on your own laptops, which, because of the campus firewall, it'll only be accessible within the room, but still, just be careful about what you have in that directory while you're hosting it. So let me just, I created this temporary folder. Let me just make sure there's nothing in it. ls/la to see all files, including hidden ones, in a list. And we see that there's nothing there. Okay. I'm going to make a file called index.html. And let me add some content into it. Hello. Welcome to lecture 8 of ECS198F. Okay, and then I'm going to run this command. which says python-m http.server. And again, feel free to try this on your own laptops. Just make sure it's in a clean directory. And I'll hit enter. And you can see that now we're serving HTTP on port 8000. We'll talk about what that means in a moment. And let me go and browse to it. So it said HTTP. So what this means is it's hosting on all interfaces. So we were talking about different types of network interfaces, right? This notation refers to any. It's a wildcard essentially. So it refers to all network interfaces. And so the way that we can try to access it is using our loopback IP address. So loopback is 192.168.0.1. Any traffic you throw at the loopback interface will go back to you. It's kind of like throwing a ball at the wall, just bounce back to you. So when you on your own laptop and you send traffic to 127.0.0.1 or to localhost or to loopback, they all mean the same thing. That traffic gets sent right back to you. So we saw that this traffic is on port 8000. So let me just append :8000. And hit enter. And so what this request should do is it'll send a web request to this laptop on port 8000. And you can see, yeah, it says, hello, welcome to lecture 08 of ECS198F, which is exactly what we typed in, right? The point of this exercise is to kind of showcase a very simple type of server. Was anyone else able to get this working? Was anybody able to not able to get it working? Okay. So the point of this exercise is that now if you run this command, run this Python command and access your server, you have proof that you've set up a server on your own laptop. And it's networked and everything. And because it's listening on all network interfaces, that means that I think hypothetically if you typed in the IP address of this laptop and added port 8000 to it, then you should be able to actually access this web server. So can you add the tmux tab? I have no idea how to use tmux. Okay, I'm going to look for the IP address again. Let's see, EN0 100.126.202.140.
Just like go.
Oh, okay.
It's coffee.
1,000. Feel free to type this in on your own laptops. If you can't read it, it says 100.126.202.140:8000.
Mac OS will block that by default.
Can I allow it? Okay, that's fine.
You fool, I'm hacking into your Mac as we speak.
We are teaching penetration testing, so if you take Ethan's laptop down while he's teaching that, you get extra credit. Okay, so try browsing to that IP address. Or is it able to work?
We'll see.
We'll see.
Well, so
There's-
far, none yet.
There is a chance that the campus firewall is blocking it off. Oh, the IP address is over here. 100.126.202.140:8000.
But do you have to be like the same like network? Because
You would, yeah.
I think it's CG NAT there. It's not going to allow it.
No, but we're on the same access point, so I have to do that.
No, the same access point is still not allowed.
Okay, interesting. Well, thank you, Jerome, I guess. That's a good thing. I guess it is security.
Can we specify that we only want to host on loopback?
You can. I forget what the syntax is, but you can definitely look at the let me just type dash help. If that helps, gives anything. Yeah, you can give the bind address. So I think if you do dash b, probably 127.0.0.1. Yeah, or localhost, yeah. So again, 127.0.0.1 is your localhost. So this is telling Python to only host the server on your local interface. So I'm going to hit reload, and it should fail. Like, in fact, let me just make it clearer. I'll try browsing. Oh, did it actually work? Wow.
I don't think so.
Okay.
It's not gonna
Yeah, it's not going to work. So it's just going to stall because we're hosting this only on the localhost interface, not on my Wi-Fi interface, which is why it's not going to work now. Questions? Okay. So suppose we had a server that is hosting both a website and SSH, right? So currently, right now, I'm hosting a website, but let's suppose I also had SSH. So again, I don't know if we've mentioned it, but SSH is secure shell. It's a protocol for configuring for getting a shell on another computer remotely and securely. So, for example, if you had a web server that you needed to configure from a different computer, then you could have an SSH server running on that web server so that you can configure it from your laptop. So that way you don't need to always have a keyboard and a monitor plugged into that computer. You can just access it from your own terminal, SSHing into that server. So when you communicate with that server, suppose you're an administrator and you're not trying to access the website, you're trying to access SSH. You're trying to configure this computer over the terminal. You're not trying to access it through your web browser. So how does your computer tell the other computer which service it's trying to access? How does your computer tell the server that you're trying to access SSH and not the web server? The solution is that in the same way that we use subnet masks in order to identify the size of a network, we're just throwing more numbers at the problem, really. So the numbers that we're throwing here are ports numbers. You can see that there's a whole list of ports that you can find on Wikipedia. There's a whole list of ports that you can find on. Oh man, check this recording. Yeah.
I think it's still recording. No. Okay.
Didn't we cut that it stopped recording?
Okay.
Do you want to stop it and then do a new one and then stitch them together?
I don't know why it's doing this. This is so annoying. It's just, display capture. Okay, I think that works.
Okay. So I lost my train of thought. Okay, so there's a whole list of ports that you can find on the internet. Just like look up list of ports, and there's a Wikipedia page that lists it very nicely. We see that 22 refers to secure shell or SSH, and port 80 and port 443 refer to HTTP and HTTPS respectively. So these are these bottom two ports are the web ports. That top one is SSH. And so the solution here is say, I want to access 192.168.0.10 on port 22 with the colon. Do not forget the colon. And that specifies that you're trying to access specifically SSH on that computer. And remember this over here, had to type in port 8000. And the reason we had to do that is because we were trying to specify which specific port we're trying to access on this computer. That I believe will work on macOS, right? I just did committed heresy. I used the cursor to switch tabs on. Oh, it doesn't work. I thought it.
No, I don't think these flags allow us.
Ah.
Or not even.
Just netstat.
There you go.
Okay, you can type netstat on your computer. You don't have to add any flags of any sort. And currently, I have the HTTP server that's still running. And let's see if we can find port 80. You can also grep, port 8000. These are all
too many things running on.
Yeah, these are all the connections that are being initiated. Local address. Oh, okay. Let's see. Oh man.
Time to hack my machine. So many things running. It's probably somewhere there.
Where are you running?
No, those are all like webs. Like if you have browser tabs open, then those show up by default on netstat because your computer is connecting to someone else's. The point of the flags is to minimize it to just the things that are connecting to you. This isn't fun to look through. Let's see. Is there any sign of 8000 at all? Maybe I should have used my laptop after all. Okay, anyway. Yeah, we could grep it, but the problem is it streams. It's like it doesn't give a single output. It like continuously waits for output. We can try it. We can try grep. It'll take a little while. Yeah, put it into a file.
No.
What were you saying?
Just upload to the file because
Okay,
it takes
sure.
forever. There you go. We'll just wait until it's done.
Any questions so far while we're waiting? I'll try to wrap up this part soon.
Can you see if we need the files?
Yeah, until it reaches that very bottom line, which
Until it reaches the
End
end
of
of the
file.
program.
You said that this is like live updating, right?
It's live update when you run it, so there you go.
Start that with
Okay,
Okay, cool.
we can also do less NS, and then let's see, 8,000. Oh,
Oh,
it's
that's
not
fine.
even there.
I wonder why. Okay, well, if you're using, I was gonna say if you're using Linux, but I don't think that caters to a majority of you. Yeah, okay, I guess this example doesn't work great on Mac OS.
I don't know what to tell you.
Yeah, whatever. So if you're using another system, or you found the flags that I will not look for right now, but maybe I'll post them afterwards, to just list the open ports on your own laptop, on your own computer, then you would see port 8000 is open because currently, I don't know what I just did. I think I just, your Tmux bar went away.
My Tmux session.
Okay. Because you currently have port 8000 listening on the web server, so you would see that as listed as one of the ports. Okay. Yeah, I guess that's all I have to say about that. So just know that there's IP addresses, there's networks, and a single IP address, a single computer can host multiple ports, can host multiple, in other words, they can host multiple services. And each of those services can be identified by a different port number in order to not conflict with other services. So this is how we prevent SSH from conflicting with web. We isolate their ports so that web will only receive traffic on port 80 or port 443, and SSH will only receive traffic on port 22. So it's separating their purposes to make sure that if a computer wants to communicate with just one of those services, they can specify which service they want to talk to. All right, any questions? I guess something good to mention is that, yeah, go.
Is that like in the packet header that they send when they communicate like what they want to talk about?
Yeah, so the packet header is the part of the, so headers in general are parts of data that specify the source and destination. That's generally what they have in there. So if you're looking at we were talking about IP addresses, right? Internet protocol addresses. So in the header for an internet protocol address, you'll have the source IP address and the destination IP address. If you're looking at specific, we're talking about port 22, right? Port 22 refers to port 22 of the transmission control protocol, or TCP. So that's a specific, I guess, like behavior of the traffic flow. So it guarantees that any packets that are sent are in order and haven't been corrupted and things like that. So it basically, it's great for communication for things like SSH, where you want to make sure that the data that's being sent is not being, like glitched out on the way. So it's not like having bits that are missing or data received out of order. So port 22 is written inside of that TCP header. So it tells you, so in that header it says the source port and the destination port, in the same way that you would have a source IP address and a destination IP address. There's another type of protocol for sending data, which is UDP. So again, TCP guarantees that in-order delivery. So it means that if you send a packet 1, packet 2, packet 3, it doesn't get received as 2, 3, 1. It guarantees that it's received as 1, 2, 3. And a UDP is a little bit different than that. So it forgoes those checks entirely. It just makes sure that the data is received and is transmitted. That's all it really cares about. And so it's great for applications that are that need really high speed, but where it doesn't really matter if certain glitches happen. Like, for example, if you're on like a Zoom call, raise your hand if you've been on a Zoom call and you've heard like someone's voice just like glitch out and just like, right? Yeah, that's like everyone. That's because Zoom uses UDP, I believe, for its communications, which means that it doesn't really do those checks to make sure in order delivery, because it just cares about the speed. Things like web and SSH, they don't prioritize speed, they prioritize that the data is correct and uncorrupted, and so that's why they would use something like TCP. And you might see that become somewhat relevant in certain pen testing exercises, but yeah. Okay, any questions? I think we can hand it off then. Or, yeah. If there's any questions, feel free to put them in Discord.
Alright, let's double check recording is going. Alright, so this is the module on pen testing. Probably the module that you may be most excited about. So today we'll talk about a very introductory basis of what pen testing is, and we'll talk about some of the techniques that we use in the real world. So, who can tell me, what is pen testing?
Guesses. Does it involve
Any
pens?
guesses? Yeah, do they involve pens or testing pens or any of that? Yes.
It's kind of like shorthand for penetration testing. It's kind of like how you try to get into like a network of some sort.
Okay, how to get into a network? Any other ideas? What else does penetration testing involve?
So I should just go into the NSA's network for fun.
Okay, so penetration testing is a very broad term for testing vulnerabilities, not just in networks, but in any systems in general. So they could be networks, they could be physical, like you have one machine that you're trying to test to make sure they're secure. It could be a website. So all of these would fall into penetration testing. We traditionally have two teams in terms of cybersecurity. There's the red team, which is what we've always considered as the default penetration testing. You're trying to hack into something, break into something. And there's the blue team, which is the defenders, preventing these attacks, whether it's from good people who are doing the penetration testings, or it could be from legitimate, like, malicious actors. But recently, we've actually had a third camp of penetration testing activity called purple team. And purple team is a combination of red team and blue team. And who wants to guess what purple team pen testing does?
Wasn't it like red, black, and gray, or am I losing track of that? These are the ones that find vulnerabilities and then they're reported, but they're not.
So you're thinking things like white hat hacker and black hat hacker and those all the different
Is
colors
that
of
the
hats.
same idea, though?
It's not really the same idea. Yeah, so traditionally, because red blue comes from the military term, so military exercises, you had the red team and you had the blue team of like doing physical military exercises on the board. So that's where the term came from. And these hackers was really an internet thing. And so those were the red hat, black hat, white hat, like gray hats, somewhat ethical, somewhat unethical.
Yeah.
Tag yourself.
Tag yourself. So who wants to venture a guess? If you have blue team, you have red team, what's purple team? Yes.
Both like a defender and attacker. I think because red makes purple out.
Okay, so how would that work in an industry?
Well, wherever they assign it, I guess.
Okay, so purple team is very interesting because instead of just attacking where you're essentially coming from the standpoint of not knowing anything about the system, not knowing anything about the network, you actually talk to the defenders and you ask them, like, what is important for us to look at so we don't waste our time going down, a tunnel where actually it's all secure. So that's why we see a lot more purple team pen testing nowadays. So it's very focused and very narrow. They talk to the defenders. The defenders know what the red teamers are doing. The red teamers know that blue team's looking at things, making sure everything's correct. What do people think about the advantages? Why would you want to have a red team attack versus a purple team pen test attack? Yes.
Because usually if anybody want to try to invade the system, they don't have details about what the defenders are doing.
Yes.
So they're just going to be try random stuff.
Okay.
But you also want the purple team just to make sure that if there is something you cannot take the risk of at all. So you want to give the vulnerabilities to these attackers so they can just heavy test on it.
Yep.
Also you want to have an overall secure system. You don't want somebody to try something random that is basic and then just get it the system for that.
Exactly. So you traditionally look at red team pen testing, and it's very common because you can say the blue team could tell you, oh, these are the things that are insecure, these are the things that are secure. Focus your time on the insecure stuff. Exactly. The whole point of a penetration testing is to forcefully try and make sure you've covered all the aspects of your system and all security aspects. So if we're just going to focus on what the blue team thinks is insecure, you might actually miss something that's even worse. Like there was some gigantic hole in your system that's overlooked because the red team never looked at that.
Wasn't there the everlasting thing that they used to do for Google servers back in early 2000s, where they just keep begging the servers till they kind of crash? Wasn't that half of the?
Yes. So.
I forgot what it was called. But they just take it from multiple machines infinitely.
Yes.
The whole server will just be consumed by machines that are just holding service without being actually using it.
Right.
That was one of them, but I don't know.
Yeah, so that's an advantage of red team, but purple team, again, like you have a concentrated number of resources to actually target something that you might find is vulnerable.
You're referring to distributed denial of service or DDoS.
That one they did not actually like think of the case where people will just be using the service. So when a hacker tried to kind of like achieve that together, they tried to just ping it all together at the same time from the machine infinitely.
Mhm.
So they kicked out all the users from the service because
Yeah.
all the machines were just infinitely catching these servers.
Yeah. It overloads the network.
Yeah, I don't know what it does, but like I know they just did like a fake something and then it never.
Alright, so we're going to be doing an actual pen testing exercise over here on Hack the Box if it loads. But I want to make something very, very clear, right? We're learning about actual attacks that you can actually do in the real world. And executing these attacks is against the law unless you have permission. And these are the 3 words that will be emphasized throughout the quarter. Stay in scope. Stay in scope. Stay in scope. What does that mean? That means do only what you're told you're allowed to do. So if someone comes and tells you you can hack the web server, then you can only hack the web server, nothing else. You will be told this is what you can do and this is what you can't do. Follow the rules or it's against the law and you can go to jail. It's very, very important. Stay in scope. Okay, so let's talk about how we execute a normal pen testing. So there's a new university over here called Davis Institute of Technology. They're a new university, they don't know what they're doing, they've just set up their IT systems and they've hired all of you as pen testers to go and test out the security of their systems. What's the first step you should be doing? And the hint to you is, we've already covered this in a previous lecture. What's the first step you should do?
I alluded to it earlier today, I guess.
Go ahead.
Find the subnet mask.
Find the subnet mask. No. Yes.
Like we want to ask them what specifically we're supposed to be testing.
Okay, so talk to the client. Yes, you should always talk to the client, ask them what they want to be tested. Yes, what else? This is
Is it the very first thing that they gather, we collect whatever data that's there about them, and we got what was the
perfect. First step, reconnaissance. So, what does that involve? This lecture, OSINT. Look through their websites. Look at what things they have. You want as much information as you can get before you even get to attacking their systems, right? You want to know, just on the World Wide Web, what websites do they have? What machines do they claim they have? What's interconnected?
Who's the team to,
Who's the team that's controlling this, right? I can look at who is, right? I can look at who is the who owns the website server. That information might be public, right? Where are these servers located? That's all good information that we can use. Now, going back to scope. Is this in scope?
yes, because we're not using any data that is private, basically, it's public data.
Right? It's public data.
Yeah.
Therefore, it is in scope. Yes, you don't need permission to do OSINT. But part of reconnaissance is not just OSINT. You can actually do things like social engineering. You can try and call up their staff and be like, I'm this employee, I'm the chancellor or something, can you reset my password? This is all part of reconnaissance. Is that allowed?
It's not because we're stealing identities at this point.
Okay, you don't think it's allowed. Who thinks it's allowed? No one thinks it's allowed.
I think it's allowed.
You think it's allowed? Okay, my browser. Oh.
If they allow you to, then it is. If it's not, then no.
Okay, exactly. Good point. That's where scope comes in. If they specifically say you're allowed to social engineer our staff, then you are. But most of the time, the answer is no. Don't try and call people up and be like, I'm the chancellor. Please reset my password. That's not allowed. Okay. So, This is a challenge on Hack the Box. We're not going to be doing any reconnaissance. There's nothing interesting on there. So we'll actually just start to the second phase of the attack. What's the second phase? What comes after reconnaissance? Who knows? Who has a guess? Okay, you've looked at their websites, you've looked at what systems they have, and now you're armed with information. You're at their site, and they've given you this IP address. 10.129.44.236. You can attack this IP address over here. What do you do now?
Ping it first to see if I have a connection with it.
Okay, let's ping it first. I like that. Ping this first. Oh no.
Are you on the VPN?
Oh shoot, yes. I should go on the VPN.
Hack the box VPN.
Yeah, where's the VPN? Okay, what should I do? Ping the machine.
Because if you don't have a connection, then you need to build one if you can. Not
Do you have OpenVPN?
Yeah. What were the files called? Machines. Okay. So let's try pinging that again. No.
Do you have to run it with sudo or
That might be the case. Whoops.
cannot allocate tunnel dynamic?
I think that's working.
Yeah, it's up.
Okay, ping the machine. It's receiving traffic. Now what do I do? Something's on there. It's running. It's returning our ping requests. Who has an idea? SSH into it. What makes you think SSH is on this machine?
I don't know, is the port open?
Is the port open? Okay, how do we determine if the port is open?
That's one command.
Huh? Alright, so
ping with the port.
ping with the port. Okay, so I'll introduce a better command for you. I think this also requires sudo, so we'll introduce this new thing called nmap.
Network map.
Let's try to see if that wants to work. So it'll probably take a while. So the second thing we want to do is scanning.
Oh, that gives you the whole ports thing.
So what this does, and I'll also run a concurrent nmap. Oh, okay, here we go. So that's what nmap does. It scans a bunch of ports on that particular IP address. You can give it a subnet mask, and it'll scan a range of IP addresses, and it'll tell you what ports are open, and they'll try to find what information it can gather. So the -S flag tells you this is a TCP connection, so a SYN connection. The -V flag tries to give you versions. So that's how you get, it says HTTP title, security dashboard. It thinks it's a Unix or Linux web server. It thinks there's SSH running Ubuntu, whatever, 8.2 open SSH on there. So we'll try to get some of this version information. The -C tells it run the standard script against that. So these are, again, what's it called? These are actually TCP connections, so I can also do a -U. So -U says run against UDP. Normally you try to do both of them, just to make sure you're not leaving anything out. So you scan something, you see 21, 22, and 80 are open. What should I do next?
Another question?
Yes.
Doesn't it already say that SSH is open?
Oh, SSH is open.
You just said that, that's why it was going.
Okay, so SSH is open, FTP is open, HTTP is open. What's the next logical step from here? There's a hand, yes.
Every software when you update probably patches some security hole. So let's look at what kind of security hole does like OpenSSH 8.2 have.
Okay, look at the security holes, okay? That's actually a third step, but we're not even done with the second step yet. Third step is attack. So look at holes. That's part of attacking. Yes.
Maybe we can poke around the FTP server.
Poke around the FTP server, okay? Let's try that, FTP.
Is anyone here not familiar with FTP?
Okay, so we should talk about FTP. FTP is the file transfer protocol. As the name suggests, it's used for transmitting files. man FTP will tell you file transfer protocol. You literally try to talk to a host. Sometimes there is no login, and sometimes it's anonymous login, so you can just FTP connect and try to retrieve files from a server. And sometimes it is protected. So in this case, it asks for a name. I don't know. We'll try, I don't know, root. Please specify the password. Well, we'll just guess the password. Doesn't look like it's letting us in. So it looks like it's protected by some password. Doesn't look like FTP is going to give us any information. What else can we do? Yes? We can look at the HTTP. We have a website. That's fantastic. Part 80 is open over there. It says gun core. Okay, so there's a website on here. What should we do over here? So I will let you know that part of scanning is looking at all websites. And sometimes these websites, these might be internal websites, might actually have information that leads you to go back to some of these first steps or these beginning steps. So you might be able to do more OSINT or reconnaissance based on something that you found. And so these steps are a guideline. They're not something definitive. You shouldn't just step 1 step, step 2, step 3, step 4, step 5, and be like, I did all the steps, I'm done. You might have to rotate between them. So looking at something interesting, you might have to go back and do more due diligence at the reconnaissance step. So there's OSINT, so this is part of intelligence gathering. I'll put this up here. Intelligence gathering. Websites, Nmap. There are other services over here like Nessus, which would look at websites. So there's a lot of things that you can do for scanning. So what do we do now on this website? Well, browse it, exactly. First thing you should look at is, we tried looking into this FTP server. I didn't know what user there is. There's a user right there. There's Nathan. So this might be helpful later. Looks like I'm already logged in. Very helpful. Let's look at random stuff.
You should press logout.
I should press logout. I don't think that's a good idea. Not yet. Let's look at, so there's something called security snapshots, IP config. Okay. What did I just do? IP config, okay. Huh. This is interesting. Tells you some information over here. Can I zoom in? I can zoom in.
Now you can find something to mask.
Find some mask. Okay, so you have some information over here. Tells you the IP of things. What happens if I look at network status? Oh wow, tells you everything. Looks exactly like the output I had. Net stat and everything, running totally interesting stuff. So let's say you've looked at all this stuff. Do we look at this page over here? Okay, that one wants to just load. Okay.
Maybe we should download all the pages before they try to kick us off.
Okay, you want to download all the pages before they kick us off. That could be something you can do. So we've looked at some of these pages. You look at, oh, interesting. There's this packet analysis, 5-second PCAP analysis. Let's download this. What does this give me? Let's open this file. I think this will open Wireshark. Okay. This actually gives you interesting information. It tells you there's some ICMP requests going on. There's some UDP stuff going on. Very interesting stuff. Where do we go from here? What can we infer from this website, first of all? What can we infer from this website? Yes.
Username so far.
Okay, we've identified a user called Nathan. What else do we know here?
There's another hand. You also have your hand?
It gives a bunch of network information.
It gives you a bunch of network information. What does that tell you? Yes.
Nathan's most likely some sort of a network admin.
Okay, Nathan's most likely some sort of a network admin.
You also have your hand up?
Nothing else.
There was one that tells you how many attempts you get, and stuff like that. The very first page we had.
The very first page we had on the dashboard. Over here.
It was saying failed login attempt and all of that.
Failed login attempts. I'm clicking around. There's literally nothing for me to click over here.
Okay, doesn't this like give you information about?
Okay, so you think 357 failed login attempts. There's a bunch of security attempts, port scans, someone scanning these websites.
Never mind then. I thought that this like the number of times you get before you.
This could all be helpful information, but my question is, what do you infer from this? Like, how does this help you do an attack? So we scanned everything. We've looked at SSH won't work because you need a key. We've looked at FTP. FTP doesn't work. We've looked at this website. We've looked at everything. We've scanned everything. Now it's time for attacking. How do we start an attack here? What can we do? Yes.
I see that it's HTTP.
Okay.
You automatically get logged in. Meaning that there either is a default password or you can just see the password in clear text.
Right. Default password or password in clear text. I love that. I love that you said password in clear text. What does that mean? That means it went over the network without any encryption. And somewhere over there told me that there's some 5-second PCAPs over here, network captures, that was just on this machine, that I just downloaded something over here. So maybe there's some information over here that would give me some plain text information. I don't see anything, everything's UDP. But I'll give you everyone a hint. If you look at the URL at the very top, it says data/1.
Oh, we tried data/2.
Okay, data/2. What will that do? Okay, data/2 didn't work. What else can we do?
Data/0.
Data/0. Oh, okay. Let's try data/0. Start counting from 0. Oh, we got a page. Let's download this PCAP. Let's see what this. Oh, 0.pcap now. Oh, wow. There seems to be a lot more information over here. All right. So we see a lot of TCP. We see some FTP requests. Well, we know there's an FTP server on here. So let's actually filter for FTP. Ooh. What does that show you? Asks for a user, tells it Nathan, says please specify the password, and I see a plain text password that just showed up. Can I zoom in?
I'm not sure.
Oh, I can. Nathan, please specify the password. Buck3th4tform3 exclamation mark. Exactly. Okay, so let's actually just zoom back out so I can actually copy. Where's the data over here? Here we go.
I think you can copy it.
Let's copy a C string. Oh no, copy as a
You can
printable
copy it from the
text.
repository.
Well, I can do that too, but let's see. Let's come back over here. So we said Nathan. Shoot. Let's come back over here. Name, Nathan. Password. Hopefully that was the right password. No. What password did I copy? Oh, too much information. Okay. So that's the password. Let's try again. Nathan. Password. Login successful. Okay. We've logged into their FTP server. Now what do we do?
Transfer file out.
Okay. What do we do? So we transfer files out. How do we look at files? So this actually looks like a typical Linux system on FTP. You can do things like ls, I believe. ls. Okay. There is a user.txt. So that's actually just so because it's a file transfer protocol, so you can only retrieve information. So things like get user.txt will bring this back to my machine, I believe. Okay, so I should have got user.txt. Let's see if I did. I got user.txt. I believe if I now come to this machine over here, no. Submit flag. There we go. So we got the user.
How do you tell there's a flag? It's not like something like flag and open braces.
Right. intuition, essentially. Like, that's the only thing that's out there. It's user.txt, that's what you want.
For platforms like Hack the Box and Try Hack Me, the user flag is always given by user.text, and then the root flag is always given by root.text. That's just the convention they have for all the challenges on their system. So
if you get the file, you're good.
Okay, yeah, so I got the file, so I got user.txt, and obviously it's not happy with me yet. It says submit root flag. What can I do? Yes.
You can try using the same username and password on SSH.
Try the same username and password in SSH, since there's SSH. Okay, so SSH Nathan at, what's this IP address? Here. Let's actually use this so I don't save it. What was the password again? I should have saved this. Okay. Okay, I'm in SSH. What should I do now?
List files.
List files, okay. We've got the user.txt, same user.txt. We want to be root. List the hidden files, okay? So let's do my favorite, alter. Nothing, everything's going to dev null, so it's just basically empty information.
So like cd to the root directory.
cd to the root directory, okay.
Could be funny stuff in any of those folders.
Could be funny stuff in any of those folders, okay. So let's actually go to the standard user. There's nothing there. You can find things, I will, let's
Can you see the home and see if there's any other users?
cd into home. Nope, I'm just the only user here, only Nathan.
Wait, they put a password on their sudo.
Ah, good question. So let's just let's just switch user, so that will bring me to root. I'll paste the same password again, hopefully. Nathan is not in the sudoers file. This incident will be reported. Oh no, we got into trouble now. We have to go report back to the blue team.
Oh, poor David.
Poor Nathan. What should we do now?
Let's just repeat this 10 times.
Repeat this thing 10 times. Okay, that's definitely not the right thing to do. Huh?
I'm saying that's a good way to get him in jail.
It's going for him to get into jail. I see.
How do you see who
We're not trying to
is in
penetrate.
this file?
What?
How do you see who is in this file?
If you have sudo access, you can access the sudoers file. But since we don't, so we don't know who's in there. So part of an attack is something that we can do called privilege escalation. Something that we can do over here is this thing called linkeys. So linkeys is this thing called Linux privilege escalation awesome script. So if you execute this script, it will try to find a bunch of vulnerabilities that are on the system. Other things for privilege escalation exist. Something like Metasploit is a very useful tool for both attacking and doing scanning. But for this exercise, I only have a couple more minutes, so you can actually pull this down, move it to the machine, and then execute linkeys, and it will give you some output, and then you should be able to find an executable. I don't have the answers here, so I'm just going to cheat. Where is this? So if I actually go to /user/bin/py, okay, so let's just do, okay, that's too much. So let's just grep this for Python. What will this tell me? Python 3.8. What you should see is Python 3.8 is set as executable on root. So if I try to run a Python 3 script over here, and I say something like import OS, os.set_uid to 0. That's setting myself to root. os.system execute bin bash. I'm in root. So why did this work? That's because Nathan decided to put the Python binaries as root access. So when I execute this, instead of executing Python normally in my user line, I was able to execute this as a root user and therefore do this kind of thing. And when I told it to execute the shell bin bash as root, it gave me a shell for bin bash on root access. So now I'm in root. And you will be able to find this out on LinPs. That is correct.
LinPs will produce like a lot of output, and you just look through it and see, oh, this is vulnerable, try this. Oh, this might be vulnerable, try this. And then from there, you can just start Googling and figuring out what else is going on.
So I have 2 more minutes, so I'll quickly go through the rest of the 2 steps. The fourth step is you would do something called post-exploitation. That could be things like looking through command and control or some sort of persistent attacks. And then you also have to do cleanup in post-exploitation. So whatever you've done to the systems, if you're actually doing a penetration test, you don't want to leave behind artifacts. So you did all these things successfully, you should clean up and not damage the systems further. The whole point of you being hired as a penetration tester is so the company knows how to remediate vulnerabilities. You shouldn't be introducing more vulnerabilities in the systems. And the last thing, everyone should know what this one is. It's called reporting. If you don't do this last step, none of these 4 steps have occurred in the client's mind. So that's why we make you write reports. They're very, very important in the industry. And
What if you did it and you didn't report?
And so,
well, proof or GTFO. That's the hacker motto.
So must have proof. So everything that I've done, you should have been taking screenshots, documenting this. HackTheBox actually does nice write-ups. This is where the answer key is. So this is sort of their write-up for this exercise. They tell you exactly, right? You went through Nmap. Let's look at FTP. Let's look at HTTP. You see, most of the page is just screenshots. Screenshot what you've looked at, what you've done. This is an answer, so it only contains like right information. But in an actual penetration testing report, I would also expect you to tell me what you've done that didn't work, right? Maybe you tried your FTP at the very beginning, didn't work. You tried SSH, didn't work. All these different attacks that didn't work are helpful to the organization as well because it knows, oh, we were successful in preventing that type of attack. So things that don't work and things that work should be on the screen. Lots of screenshots. This whole thing is 6 pages, but majority of it is in text. But instead, screenshots and pictures.
And our reports and these things, you want us to kind of put every failure attempt or just the ones that actually make stuff because you're just going to be dealing with a bunch of stuff?
Put as much as you think makes sense, right? A couple failures, explain those failures. Why did you try this attack and why did you try this attack? That's what I want to see. And again, if you've not been paying attention to this whole lecture, 3 words, stay in scope. That's the end.
Reporting what worked and didn't work from